Okay, so this is a problem involving the de Broglie wavelength. 29 talks about the wave particle duality of 29. Talks about the de Broglie wavelength. I think Compton scattering is in this chapter, and Heisenberg uncertainty principle. I think photoelectric effect. But anyway, what it talks about is that particles act like waves. There's a section in your book that has this image of electrons scattering through two little slits and forming an interference pattern as if the electrons were waves. And it turns out that that's simply the nature of matter. When at our scale, at the macro scale, what some people like to call it, we don't really see this. If I walk through that door, or if I throw a ball through that door, that ball is just going to go straight through that door. It's not going to be deflected left or right. It's not going to get any additional momentum left or right or anything like that. But if I squeeze that door, if I reduce the dimensions of that door to something very, very, very small, and then I shine light through it, light will create a diffraction pattern. If it's one slit of width W, it'll create a diffraction pattern on the other side. If it's two slits, it'll create this pattern of dark and light fringes, as described by the Young's double slit experiment. Okay, so this is admittedly a strange idea that particles act like waves, and waves act like particles, but it's reality. Okay, so what this problem is asking you to do is, let me read it first. An electron starting from rest accelerates through a potential difference of 418 volts. What is the final de Broglie wavelength of the electron, assuming that its final speed is much less than the speed of light? Okay, so the first part is all right, because the first part is all what we've done already in some of the earlier chapters, 20, I think, 19, where we're talking about a voltage, and we're talking about an electron being accelerated through a voltage. So that's like a ball rolling down the hill of height h. If you've got a ball here rolling down the hill of height h, it's got some potential energy here that's going to be converted completely into kinetic energy by the time it reaches the bottom of the hill, which is which is a distance h below its original position. Okay, so if it has, say that it has zero kinetic energy at the top of the hill, by the time it gets to the bottom of the hill, all that potential energy, that gravitational potential energy, mgh, will be converted to kinetic energy. So if I wanted to find out what's the velocity of this ball, well, I know that kinetic energy equals 1/2 mv squared. This is the gravitational potential energy of the ball. I can just solve this for v. M's cancel. I get gh, 2gh over the square root. The square root of 2gh is the velocity, okay, at the bottom of the hill. So that's how that's solved in the gravitational picture. Okay, the electric potential is the electric picture is not that much different. I have a voltage drop here. Say instead of a ball, I have an electron, and instead of a hill, I have a voltage A, a voltage B. And and I have this electron. By the time this electron rolls down through this, or passes through this potential difference, okay, which I just represent as a straight line, okay, it's going to have an energy, E, say kinetic energy, E, equal to its charge times the difference in the energies. That's how much kinetic energy it's going to gain. If it doesn't have any energy at the beginning, all of this, if it doesn't have any energy in the beginning, or if you do have some energy in the beginning, you just tack it on at the back here, okay? But say that its energy is 0, just to make it simple. So the kinetic energy, after it accelerates through this potential difference, is going to be the charge times the potential difference. The difference between VA and VB. The same thing in the gravitational picture. It's the mass times the acceleration of gravity times the difference in the height. Instead of difference in height, I have difference in voltage. Okay? So that's what's happening in the first part of this problem. The electron is starting from rest, accelerates through a potential of 418 volts. So that means that its kinetic energy at the beginning, at the end of that acceleration, if it's starting from rest, which they tell me that it is the charge of the electron, E or Q, whatever you want to use, times the voltage. That's it. There's nothing more to that. Okay? And that voltage is 418 volts. Okay? So they said that assuming that its final speed is much less than the speed of light, who cares? Okay, what does that bit of information tell us? What does that mean? The final speed being much less than the speed of light means that we don't have to use those equations from, or that formalism from special relativity. If it was approaching the speed of light, then we'd have to use relativistic equations, relativistic energy, relativistic momentum, relativistic mass, relativistic, etc. Okay? But we don't, because it's not approaching light. So this is a implicate. This tells us that our kinetic energy can be simply 1/2 mv squared. Okay? All right. So please don't confuse these V's. This is my voltage. This big capital V is my voltage, and this is the velocity of my electron. This is the mass of my electron. This is the charge of my electron, and that's the voltage that it was accelerated through. Okay? So they want me to find the final speed and the final speed. So let me just solve this for V. So that's going to be 2e V for voltage divided by m, the mass of the electron, and then I can just take the square root of both sides to find V. Alright, so that's my velocity. Okay? Now they want us to find the de Broglie wavelength of an electron. Now, as I was saying before, this is a strange idea of particles having wave-like behavior and and waves having particle-like behavior. But as I said, it's a reality. So, and every object has its own wavelength, and this is how you calculate it. It has its own. Every object has its own de Broglie wavelength, and this is the way you calculate it. It's related to the momentum and Planck's constant. Planck's constant is just h equals 6.62, I think. 6.63 times 10 to the negative 34 joules seconds. Okay? Yes. Units of action. Okay? So it's just a constant, and this is your de Broglie wavelength, and this is your momentum. And once you find your momentum, you're done. Because all you have to do is just divide h by your momentum, and you'll get your de Broglie wavelength. But we only have v. We don't have this v, speed, right? So what do we do? How do we get momentum from speed? Well, yes. momentum is mass times velocity. So we have the mass of an electron, that's 9.1 times 10 to the negative 10 to the negative 31 kilograms. And we have the velocity here, which we just calculated, is 2 times the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. And our voltage is 418 volts divided by the mass of an electron. Alright. And so when we calculate that, we get the momentum. Let me find that. Alright, so that's 2 times 1.6 into negative 19 times 400 divided by 9. What's that? Get the square root of this. Multiply that times 9. Okay, and if I have not made a calculator error, this momentum is 1.1 times 10 to the negative 23 kilograms times meters squared. Times meters per second. And I'm just gonna move right up here and calculate my wavelength. 6 point. It's Planck's constant divided by my momentum as I found here. Okay. So this is my wavelength. That's it. So I just 6.63 times 10 to the negative 34 divided by 1 point. Alright. So I got the wavelength is this. Okay? 6 times 10 to the negative 11 meters. Now notice how small that wavelength is. Okay? This is why we don't see, this is why, mechanical engineers and electrical engineers and stuff don't really talk about quantum mechanics and stuff, because they don't really have to deal with the effects of this. Because the only time the Broglie wavelength becomes significant is when your electron is passing through a hallway that's around the size of the Broglie wavelength. If the hallway that it's passing through is much bigger than its de Broglie wavelength, then the electron behaves pretty much like a particle. But when the size of the hallway or the passage that your electron or particle is passing through gets to be about the size of this de Broglie wavelength, that's when your electron is going to start to act like a wave, more like a wave, diffracting and all this kind of stuff. And you're going to have to start using quantum mechanical formalism, okay? And this is what happened with Intel. They were miniaturizing their chips to get faster and faster computers. So you're miniaturizing your chips, so your circuit boards are getting smaller, your CPUs are getting smaller, and all your components are getting smaller. Your little lanes for connecting your diodes and your capacitors and your resistors on your circuit board, they're getting smaller and smaller too. So once they get around the size of the de Broglie wavelength of the electrons, or the electricity or the current that's actually passing through the printed lanes on the circuit board, you're going to start getting these quantum effects. You can't really predict where your electron is going to go. Ohm's law is going to start failing. The other stuff that we looked at, RLC circuits, that's going to start failing. All these equations are going to start not to work. So what did Intel do? You can't do anything about this, because this is just the nature of electrons, the nature of all particles. Even baseballs have a de Broglie wavelength, but the thing is that the de Broglie wavelength is so small that we don't need to take quantum mechanics into effect, because the environment that the baseball is in, you know, the catcher's mitt, blah blah blah, is much larger than the de Broglie wavelength of the baseball. So, but what Intel was having problems with was quantum mechanical effects, and so instead of miniaturizing their CPUs or their chips, they had to go into another direction. What was that other direction? They just had to put multiple chips on the circuit board, or multiple chips on the motherboard. And so that's why you got the dual core, quad core, all of these different chips to multiple chips on the same board. It speeds up the computer because the workload is being distributed across the multiple processors. Instead of having one very fast processor, you have 4 processors that divide the load and speed up the processing. So that's where these ideas of quantum mechanics and the de Broglie wavelength come into our everyday lives. You know, there are not too many places where they do come into our everyday lives, and so that's why these ideas probably kind of feel uncomfortable at the beginning. I mean, for me, like when I was first looking at this stuff, I was like, that doesn't make any sense to me. I've never seen, you know, why does a particle act like a wave and vice versa sometimes, and so it takes a while, but that's all that a problem involves, is finding momentum and using this equation, which involves Planck's constant, to find the de Broglie wavelength. Okay, which is the wavelength of this particle at this momentum if it were a wave. Okay, so any questions about that? All right, so from this chapter, let's kind of just look at what we would be looking from this chapter. Look, what are we looking at? Okay, what I'd like you to do is understand this equation right here, 29.9, which is basically what we were using in chapter 30, which says that energy comes and is quantized. It's quantized. Okay, it comes in discrete packets. Those packets being photons. So this is the energy of the photon, and this is the energy. This is an energy photon, and this is a multiple of that energy. Okay, so this is black body radiation.
How do we know when you use that computation?
This equation right here. Oh, this equation is for the photoelectric effect, and what it is it tells us what the energy of a photon is escaping from the atom after it drops in energy. After it goes from a higher energy state to a lower energy state, it has to emit a photon.
So the 29.2 equation is when it's transitioning, and the 29.1 is just whatever energy it has at that one state.
Yeah, this is what Max Planck, when he was looking at black body radiation, he had this formula that was related to it related the intensity of the light giving off by a black body to the wavelength of that light and a certain distribution. Okay. So you won't be using 29.1 that much. It's what the main idea, the upshot of what I'm going to say, is what I'm about to say going to be. But okay, so if you have black body radiation, this is the intensity. I'm going to plot the intensity of the light as a function of wavelength from that black body. So this can be a hot pot on a stove or something like this. All right. So that's the black body radiating energy. Okay. In all directions. Okay. So it's going to radiate energy across the spectrum. So multiple wavelengths. Okay, most of it is going to be in the infrared. You know, so we won't be able to see it. But as I heat it up, I start exciting more atoms in higher energy states. So as my temperature rises, this peak rises, and so does, and it broadens. Okay. There's an equation called the Rayleigh-Jeans equation that described this. That described that. It was something like there was something up here, and then it was proportional to 1 over lambda raised to the 4th power. But see, this blows up at 0 when at very, very short wavelengths or very, very high energy, this goes up to infinity. So what Max Planck did was say that the energies have to be discretized, and he came up with another formula that involved, let's see, what was it? It was E raised to HF divided by beta T, I think something like this, minus 1. You can look that up in some of your other books. I don't think it's in your book. But in order to get to this equation where that fixed this problem of the function blowing up at 0, he had to quantize energy. And so that's where that comes from. But this other energy is what you'll be using more often. And it's E equals H times F, where F is the frequency of a photon. This describes the energy of a photon given ejected the energy of a photon incident on the surface of a metal. And what it does is it hits that metal, and it ejects an electron. And that electron has an energy that is whatever that photon's energy was minus the energy that it took to break it away from the surface. So let me talk about the photoelectric effect. Okay, so the photoelectric effect talks about light interacting with matter. Light interacting with, more specifically, metal. Okay, and so here's the story. You've got a photon that comes in. It strikes the surface of the metal, and it hits the electron. That electron pops out, and it has a certain kinetic energy. What is that kinetic energy? Where did it get that kinetic energy from? It gets the energy from the photon. What's the photon's energy? Is HF. It's whatever. It depends on the frequency of the photon. If you give me the frequency of the photon, I can tell you that its energy is that frequency times Planck's constant. If you give me the wavelength of the photon, it's Planck's constant times c over lambda. So if you give me the frequency of the wavelength, I can give you the energy of the photon. So the kinetic energy that the electron pops off at, that the electron has after it pops off, comes from the photon. Now the electron doesn't get all the photon's energy. It gets the photon's energy minus the energy that it takes to pluck it away from the surface. What's the energy that it takes to pluck it away from the surface? It's the work function, W naught. Okay? Yes, Miss Cotton.
Can you calculate the energy of a photon from just supposed wavelength and H and C?
Yep.
Wavelength. Can you calculate wavelength from, like, let's say you have a calculated value of wavelength, and then you have H and C. Does the energy of the photon help you in any way of getting a more accurate wavelength?
No, it just is the way the energy of the photon is. It's just calculated that way. It's it's just the wavelength times the wavelength. I mean, c divided by the wavelength times Planck's constant. That's
So that's the only way to find it?
the energy of the photon. Yeah, that's the only way to find the energy of the photon. Yeah. What's another way that you were thinking that might be less accurate? I think you were saying like this one would be more accurate.
No,
There was
I mean,
another less accurate way.
I was trying to find a way to calculate wavelength,
Uh-huh.
but I didn't have energy of a photon.
Oh.
So I was just, and I didn't want to use my calculated values per se.
Okay.
To get an accurate wavelength.
The wavelength. Yeah, the wavelength of a photon is lambda.
It's d sine of theta over n.
D sine of theta divided by n. Oh, that's
the diffracted angle
oh
of
no.
a spectrometer.
Yeah, that's. I think you're talking about Young's double slit experiment.
Yeah.
Okay, and so what you're really looking at is sine of theta equals lambda times n divided by d. Okay, yeah, this is the wavelength of your light. Okay, and this in this situation, in the double slit experiment, your wavelength think of your wavelength as more of an input. Okay, you're given a wavelength, and your light is traveling through two slits. Okay, and one. Okay, so it's traveling through two slits. You got a light source in the back. Just imagine a bulb here, and it's shining red. Only red, not orange, a mixture of red and yellow, but just red. So that's a single, it's monochromatic. That's important, because otherwise you have to use different math. Okay, so it comes through these two little peepholes, and because these peepholes have a distance of d between them,
Which is like
Just
300 lines per nanometer or something like that.
no, that's another that's a diffraction grating. Okay, but these are just two holes. The diffraction grating has a whole bunch of different slots in it, but this is just two slots, two holes. Okay, so you're gonna have light peeping through this hole, and you're gonna have light peeping through that hole. Okay, and they're gonna come and they're gonna hit a spot on a screen in the back. Now this is gonna hit it a little bit later than this one, because this one's got a head start on that one, because it doesn't have to go as far of a distance. This one has to just go this distance right here. This one has to go this distance, the same distance, plus this little distance right here. Okay, and I'm gonna call this distance L. Okay, so I've got light propagating like this and light propagating like this from this hole, these two different holes. Because they're going to reach at different times, they're going to be at different phases. One's probably going to be going up while the other one's probably almost there to the top, okay? Or one might be completely down. It depends on this distance right here is what I'm saying.
Okay.
This distance L. So that distance L is an integral number of wavelengths. You're going to have constructive interference. If that distance L is a multiple of half wavelengths, you're going to get destructive interference. Now, what does that mean? Constructive interference and destructive interference. When these two waves hit this point on the screen, if they constructively interfere, they're going to make each other brighter, a brighter spot on the screen. If they destructively interfere, if one is down while the other is going up, they're going to destructively interfere and make a dark fringe. And so this equation is telling you where those fringes are. Okay? How does it tell you where they're located? It doesn't tell you like, okay, this one's going to be 5 meters from the center, this is going to be 5 meters from the center. This is the way it does it. Okay? Just imagine that these slits are so small that they're just pretty much in the same. They're really, really close together. We're kind of zooming out, okay? This is a line going directly from the double slits to the wall. And this is an angle indicating where on the wall we're looking at, okay? And we've got this pattern is what I'm using to represent dark and light fringes, with the light fringes being the high points, dark fringes being low points, high, low, okay? So what this equation is telling us, this theta is telling us the point on the wall. It's like pointing on the wall with an angle instead of a distance, a coordinate with an angle. So if theta equals 0, you're talking about this point right in the middle. Okay, and as you go away from the middle, you're going to hit this second bright point. They call it fringe. Okay, so this describes all the light fringes, and this describes all the dark fringes. N plus 1/2 lambda. Okay, so this is the angle that you're looking at. This is the wavelength of the monochromatic light. This is the distance between the two slits, D, and this is a number that counts the fringes. This is the first bright fringe, N equals 1. For the second bright fringe, N equals 0. For the first bright fringe, N equals 0. For the second bright fringe, N equals 1, 2, 3, 4, 5, 6, and so forth. All right. Same thing for the dark fringes. This angle right here points to where the dark fringe is going to be on the board, on the screen. Okay. So your first dark fringe is going to be here. It's going to be at an angle of blah blah blah. Your second dark fringe is going to be right here, and so forth. Okay. And this D is just the distance between the slits, because the distance between the slits and the wavelength of the light determines the distances between the bright fringes and the dark fringes and where they're located on the board. So think of lambda and D as more parameters, and theta as being, where you're looking at on the screen, and N as the number. N counts the number of the fringe. It indexes the fringes, whether they be dark. This one is for dark fringes, and this one is for bright fringes. So that's how the equation works. Okay?
Got it.
All right. Yes, sir. So where are we on time? It's 12 o'clock on the nose?
12:02.
Okay. All right then. Well, if you guys have any questions, just send them to me through email.
Okay, so you approved my first 3